It's a pleasure to introduce Professor Sergey Levine, our last speaker for the bootcamp. Sergey has won numerous awards, but he says he doesn't really believe in awards, so I'm not going to list them all. Sergey is very well known in pioneering the field of robotics, deep learning, deep reinforcement learning. In fact, many of the papers that had breakthroughs in deep reinforcement learning over the past couple of years have major influence from Sergey. And we have the pleasure now to have Sergey show to us, or present to us, what he thinks is where the field is headed and our important directions for us to think about going forward. Please join me in welcoming Sergey.
Thanks, Peter. Okay, well, given that this is kind of the end of the day and you guys have had a pretty long day, I'll keep to things that are a little more high level, so there won't be too much math, only a couple of equations at the end. So many of you probably have seen this video or some version of this video. So this is a little humanoid learning how to run. This is a video actually from the original, or actually from a follow-up to the TRPO paper. And when this guy learns how to run, he basically just always wins. Like once he's learned how to run on this infinitely large, perfectly flat plane, that's the entirety of his existence. Like at that point, he's done. There's nothing more to learn, and he never fails, which is a very appealing prospect. Like if our lives were like this, once we figure out one thing, then we always win. That would be awfully nice. But in reality, unfortunately, things don't always work that way. So if you want to use deep RL methods to get, let's say, a real-world system like a robot to do something, sometimes it'll work and sometimes it won't. So, for example, we had some experiments where we had a robot learn how to put caps on bottles, and it could learn how to spin the cap and put it in the right spot. But if you then showed a slightly different situation, maybe now this is actually, I'm here holding that bottle in my own arm, and the color of the sleeve of my shirt is kind of similar to the gray color of the robot's arm, and it actually messes up. Like it's never seen this particular kind of setup before, and it fails to generalize. Here are some more experiments. So here this robot learned how to pour some almonds out of a bottle into a cup, and sometimes it's successful, sometimes you can show it different kinds of situations, different distractors in different cups. But here, for example, it gets a little confused there and tries to pour into an upside-down cup because it hasn't quite figured out exactly the right way to generalize. And this is sort of a little microcosm of the kinds of problems that we might encounter if we try to take deep reinforcement learning algorithms and really put them into the real world. So the trouble is that we can't really build a system that doesn't make mistakes. In fact, no matter how well we train in a narrow set of situations, there will always be something that happens that messes up that system. So maybe one of the key things to building reinforcement learning systems, deep reinforcement learning systems that can really succeed in the kind of diverse environments that we might encounter in the real world, rather than just the infinitely large flat plane of the benchmark humanoid running task, maybe we need to build systems that can actually not flawlessly never make mistakes, but actually make mistakes occasionally and then learn from them as fast as possible. So what does it take for reinforcement learning to learn from its mistakes in the real world? What is it that we need to do in order to make this possible? Well, one of the things that we should try to do is we should focus on methods that really handle diversity rather than just exclusively focusing on proficiency. So oftentimes the way that we evaluate reinforcement learning algorithms is we say, well, what is the final average reward that it achieves on the particular task that it's trained on? This is in some ways very, very different from how we evaluate other kinds of machine learning algorithms. So if you imagine, let's say, ImageNet classification, no one's ever asked, like, how well does your ImageNet classifier do at classifying this one particular image? People care about how well does it do at classifying all images of that category or a wide, diverse set of images in a test set. We should aim to build algorithms that can self-supervise, meaning they have to have access to their reward function in the kinds of environments they'll actually encounter in the real world. And Chelsea might have alluded to this a little bit in the inverse reinforcement learning lecture, and I'll talk about this a little bit more, but this kind of thing can actually be a major challenge in practice. We have to have methods that can learn quickly and efficiently. So if we want algorithms that can actually learn from their mistakes in kind of realistic real-world environments, they need to be able to learn from those mistakes quickly because you don't want them to make that mistake many, many times. If your algorithm is controlling a robot or an autonomous car or a, let's say, inventory automation system, making too many mistakes is likely to be very costly or dangerous. And of course, the mistakes need to actually be fixed. So some kind of adaptive mechanism needs to be able to look at what's going on and continuously improve. So let me dig a little bit more into this thing that I mentioned about diversity versus proficiency. I mentioned ImageNet recognition. So for those of you that are not familiar with this, this is a very standard benchmark in computer vision. It's not a reinforcement learning benchmark, it's just a standard supervised learning benchmark where the goal is to train a model to recognize 1,000 possible categories in pictures. This is a benchmark that's large scale, that emphasizes diversity, and it's evaluated on generalization. So nobody cares how well you do at classifying a single particular image. People care how well you do at recognizing objects in a very wide range of different images. In contrast to this, the kind of benchmark tasks that we often focus on in reinforcement learning, especially, for example, in a course like this one, are tasks that are relatively small scale, partly out of necessity because we need something a little bit self-contained that we can use for benchmarking. They typically emphasize mastery, so the kind of score that you report is how fast did the little ant here run, for example. And they're evaluated on their performance. So if you want to ask the question, is algorithm A better than algorithm B, you say, well, is its asymptotic performance better? Or maybe you ask, is its sample complexity better? So what can we do to kind of move towards RL settings that look more like the stuff up above and a little bit less like the more narrow benchmark setting below? Because if we have, let's say, a reinforcement learning agent that needs to, for instance, control a robot, and needs to, for example, go into the home and clean up your kitchen, it's going to encounter scenes like this, which are extremely diverse. They look a lot more like images from ImageNet than they do like the clean, pristine environment of the benchmark. Okay, so in this lecture, I'm going to tell you about 3 different projects, or 3 different kind of categories of work. I guess there'll be multiple projects in each one, and then I'll talk about some broader perspectives. So first I'll talk about how we can self-supervise diverse real-world tasks, and I'll give a few examples of some robotics experiments that we've done to try to study this. I'm going to talk about where we can get goal supervision for more complex problems, and a lot of this will focus also on imitation learning. And then I'm going to talk about how new tasks can build on prior tasks. So if you want to build systems that learn from their mistakes, one of the things that you'd like them to be able to self-supervise, you'd like them to be able to understand the goal, but you'd also like them to be able to build on prior solutions to fix new mistakes more quickly. So if you've learned how to address some mistakes in the past, you'd like to then more quickly address other mistakes. And this is going to focus on things like multitask learning and meta-learning. All right, so let's start with the first topic, how we can self-supervise diverse real-world tasks. So first, I'll tell you about an experiment that we did on self-supervised reinforcement learning with real-world systems. And what we want to do is we want to first set up a task where self-supervision is relatively easy in the sense that we can actually just write down a piece of code that evaluates the outcome and just see what happens when you have a reinforcement learning problem that really does emphasize diversity rather than just proficiency. So this is an experiment that was done in collaboration with some colleagues at Google. And what we did is we set up a large-scale robotic learning experiment. So here in this video, what you can see is a collection of 14 robots. And these robots are all jointly collecting data for essentially a reinforcement learning experiment. All of the robots are actually sharing all of their experience, so it's as though it was a single parallelized run of this algorithm. And they're all grasping different objects in front of, placed in bins in front of them. And this system was running for months, collecting very diverse data. Every couple of days, we would go in and we'd replace the objects in front of the robot so that in total they grasped on the order of about 500 different things, and a total of roughly 1 million grasp attempts. Now, we chose robotic grasping for a very particular reason, which is that grasping, unlike almost all other robotic tasks, is actually very easy to self-supervise because the robot can always figure out if it's picked up something successfully. It can just see whether there's something between the fingers or not. But I'll talk later about what happens when this is no longer the case. So here's the setup. We have a 7 degree of freedom arm with a 2-finger gripper, and it's picking things up out of a bin. And it's going to use a monocular RGB camera for this. Actually, the camera is a depth camera, but the depth channel wasn't used for this experiment, just for the baselines. The camera is not calibrated, so the robot actually has to figure out where its hand is in the image, where the objects are, and be able to servo to those objects. And it's controlling the arm continuously at about 2 to 5 hertz, which allows it to servo the gripper to the target and to correct mistakes when they happen. And except for that one bit of information, which is did the grasp succeed or not, there's no prior knowledge about grasping that's given to the system. It has to learn everything on its own. So here at the top is a diagram of the neural net architecture that was used in this experiment. So this is basically a queue function. So it takes in the image that the robot sees, it takes in the action that the robot is going to take, and what it outputs is the probability that that action will result in a successful grasp. So the equivalent reinforcement learning problem would be one where the reward is 1 for success, 0 otherwise, and then the probability of the success is exactly the Q value. So the robot would collect data by basically moving the arm according to the latest policy with additive noise. That data would be added to the buffer, and that would be used to train the policy. And then at test time, you could simply search over different actions and pick the action for which the network predicts the largest probability of success, and then continue that way every time you collect a new image. Again, you try different actions, pick the one for which the network predicts the highest probability of success, and so on. Yes? That's right, yeah. So the robot is not actually being told to grasp anything in particular. So I'll actually tell you about another experiment afterwards where there was a more concrete goal. Here the goal is to actually grasp anything. All right, and here at the top I have some pictures from the camera from each of the 14 robots. And the reason that I wanted to show this is just for you to see that actually the viewpoint of the camera was a little bit different for different robots as well. And this was part of what actually forces the network to learn to do hand-eye coordination. So it can't simply memorize where the robot's base is relative to the camera. It has to actually find the hand in the picture and continuously servo it to the objects in the scene. All right, so here's a little comparison that we did. So we wanted to answer two questions. One, can a learned grasping system actually generalize effectively to new objects? So can we do something that looks a little bit more like ImageNet and a little bit less like the ANT benchmark? And is there actually benefit in the continuous visual feedback? So should you actually consider this a sequential decision-making process, or is it enough to just do kind of a one-shot grasp selection procedure? So on the right is a video of this learned grasping system, and you can see that it's trying to grasp objects there. It takes a little while to move the gripper into position, and then it attempts to pick it up. On the left is a comparison to a previously proposed approach that also uses learning, also uses self-supervision, but only makes one decision per episode. So this method just looks at the picture, it actually uses a known camera calibration, and just decides which point is the most likely to produce a successful grasp. The open loop grasping system, this is the one that makes just one decision, had a failure rate of about 33% in these experiments, and the closed loop one had a failure rate of about 17%, so quite a bit better. And we also actually benchmarked a more traditional system that is not based on learning, that's based on actually using a depth camera to segment out objects, figure out their spatial extents, and then use a kind of a heuristic finger placement rule. And that has a failure rate of about 35%. So this shows that there is actually some benefit to doing continuous control and actually learning these Q functions. Okay, so that's maybe more for the comparison, but it's, for us, it's maybe more interesting to actually look at the system and see what is it that it actually ends up doing, what kind of decisions does it make. So here what I'll show you is a few clips of our best trained neural network picking up 4 objects that are all visually kind of similar. They're all blue and roughly the same size, roughly rectangular. And for these first 3, you can see that it adopts a very natural strategy. It puts the fingers on either side and picks up the object. But for this 4th object, it's a soft sponge, it actually pinches it in the middle. And this isn't an accident. This behavior is actually consistent. Every time we showed it a soft object, it would try to pinch it like this. So it learned actually very early on, before it even learned about geometry, even with smaller amounts of data, that material is very important, that soft things should be pinched, while hard things require you to place the fingers on either side. That was a very large object, so there it's very important to grasp it near the center of mass. And for these scissors, they're very small and very flat to the ground, so this is the kind of thing that for a depth camera would be pretty difficult. And it takes a while to find a good grasp that it's happy with. This is an object that's large, heavy, and also very awkwardly shaped. So again, it moves around and changes its mind a few times before it finds a grasp for which the network does predict a high probability of success. This is an object that's transparent. Again, it's the kind of thing that for a depth camera could be pretty hard. We tried to stress test it a little bit, so we gave it sort of a nightmare grasping scenario where we had large numbers of the hardest objects we could find, and it does a bit worse on this, obviously, because this is a harder setup, but generally does pretty well. So fails a few times, but on the whole, tends to do a good job of picking up things. Yes?
All the objects you showed, were they all part of the training data set?
So every time I was reporting numbers, so when I said like 17%, 33%, that was always with objects that were unseen during training. For this experiment, I think it's about half and half. So here we weren't very careful about it. We just wanted to just dump things in there that were hard. So the main point that I want to make in this experiment is that the algorithms themselves here are actually fairly similar to what you guys learned about in the past few days, But the task is set up in such a way that it really emphasizes diversity, that we could actually train it on a very large range of different objects and then test it on objects that it hasn't seen before, or situations that it hasn't seen before, like this extremely cluttered bin. One of the things that we tried to do afterwards is we said, well, okay, we built this grasping system using these particular robots. Did it actually learn something about grasping that actually generalizes to different robots? Like, is there something in that experience that it collected that's sort of general notions for grasping that are actually useful and portable? So what we did is we had a different kind of robot shown here on the right. These are industrial kook arms. And we collected another data set using those new robots. And then we wanted to see if we combine data from both robots, can we get away with less data from the new robot and still achieve a high success rate? So this is a picture of the training objects. As I said, there's about 500 of them. And then for each condition, we're going to test it on 6 different bins with test objects that were never seen before, and that we're going to use to evaluate performance. So in this results plot, let me explain what the different curves mean. This is studying what happens when you combine data from multiple robots. This is actually studying transfer. So the red line at the top, this is the failure rate for completely random policy. That's just a baseline to tell you what a bad grasping strategy looks like. The purple line, which is a little bit better, is what you get if you train on the old robots and then just test on the new robots. Turns out that it doesn't work very well, which is not too surprising because that network has never seen this new robot. The blue line is what happens if you train on different amounts of data from the new robot. And the x-axis here is on a log scale in terms of the number of images. And each grasp is about 10 images. So when it says 10 million, that's about 1 million grasps. And then the yellow and green lines show what happens if you combine all of the data from the first set of robots and variable amounts of data from the second. And the interesting thing here is that particularly in the middle there, when you have less than 0.1 million images or less than 100,000 grasps, actually bringing in the data from those old robots makes the whole system a lot better by up to 20%. And even at the end, once you already have the entire 1 million grasp data set from the new robot, there's still an improvement to be had from including the old data. And the only difference between the yellow and the green line is that the yellow line involves pre-training on the old robot and then fine-tuning, and the green one is when you train jointly with both data sets, which generally works a bit better. So this was interesting to us, is that it shows that, in contrast to the highly specialized policies that you get when you train on a single task, here you actually can take this data and you can use it to improve performance on tasks that are structurally quite a bit different, for example, when grasping with a new robot. Yes?
When you say fine-tuning, is it the same as transfer learning for small tasks?
Yeah. Right. So fine-tuning actually can mean slightly different things. In this case, what it means is that the network was trained on the first data set, and then it was trained on the second one. We didn't actually freeze any of the layers. We just let them all change. Yeah, so sometimes people say fine-tuning to mean that they freeze some layers, and sometimes they just mean they first train on one and then on the other. That's right. Yes? So here, the end effector is the same, but then everything from the wrist on up is different, yeah. Okay, so somebody asked before, what happens if, or is the robot trying to pick up anything in particular? What happens if we want to pick up a specific thing? So that's actually what we want to study for the next set of experiments. So the network that we've trained so far, it basically tells us how likely is a certain grasp to succeed. And we can kind of visualize it here. So these funny little green lines, they show the prediction made by the network for the success of a particular grasp. Bright green means very likely to succeed, and kind of yellowish reddish shows grasps that are less likely to succeed. So here it thinks, well, it's got a pretty good shot of picking up that dinosaur and a pretty good shot of picking up the eraser. If we wanted to pick up certain objects, for example, object categories, we'd also like to be able to predict, given a particular image and a grasp, what is it that it will pick up? What kind of object will it pick up? So for the next experiment, what we're going to try to do is build actually a semantic grasping system that not only grasps successfully, but also grasps objects of a particular category. And this is going to be kind of a generalization of the previous system, where it can actually say, I'm going to pick up a toy or a pen or an eraser. And here the self-supervision gets quite a bit more complex, because before we could always self-supervise just by seeing whether the finger's closed, but now we need to know what it is that we're actually picking up. So can we learn to grasp objects from specific categories via self-supervised data collection? Well, we can't do it entirely self-supervised, of course, because we need to know what a toy is and what is an eraser. But we can actually get away with a surprisingly small amount of human intervention here. So a very kind of traditional computer vision baseline approach would be to say, well, okay, let's detect objects in the image. Let's use some kind of bounding box detector, figure out where the toy and the Lego block is, and then only grasp within that box. This requires some expensive human data collection because you need to actually build this bounding box detection system. And the bounding boxes themselves are actually not enough. Like if you have a conventional object detection system and you want to grasp and clutter, I tell you, okay, pick up the Allen wrench. Okay, the bounding box detector, if it's good enough, will put a box like this. And now you go and grasp something in that box, what's your chance of actually getting the Allen wrench? I mean, who knows what you're going to pick up in there. So the bounding box actually simultaneously gives you too much and too little information. To me, this is actually a really good example of the value of end-to-end training. So if we train the system directly end-to-end to grasp particular categories, we don't have to worry about the fact that, well, there might be other objects in a bounding box, or our computer vision system is not good enough, or something like that. We're actually going to train exactly for the thing that we want. So here's how we're going to train end-to-end. The robot is going to use a camera. Don't worry for a minute that there's like 5 different cameras in that picture. We're only using one of them, and that's the one that's labeled with that arrow. The other cameras belong to somebody else, not ours. And the main idea here is going to be labeling objects when they're in the bin in clutter is difficult. But once a robot picks up something, it's actually a lot easier for it to figure out what it picked up. So let's label objects after they're picked up, and then set that label for the entire grasp. So every time the robot is going to pick up an object, it's actually going to show it to the camera. And when it shows it to the camera, it's going to be much, much easier to figure out what it is. So at that point, we can take a small subset of this, about 20,000 images, and have some Turkers label those. 20,000 is not very much. And then we can automatically propagate those labels to all of these presentation poses, because the presentation poses are so easy. The object's always centered, it's big, it's right there in the image, and that's how we can get away, not entirely self-supervised, but largely self-supervised, meaning that the majority of the data is actually labeled automatically. There's a little bit more detail on how you actually design a neural network to be able to do this, and we had to experiment here a little bit. So one very natural baseline approach is to say, well, before we were outputting the probability of a successful grasp, now let's output the probability of grasping any one thing. So we output, let's say, n+1 way classification, where there's n classes, and the +1 is the failure. That was a very natural alternative, and it turns out to work almost kind of shockingly badly. We experimented for a while to try to figure out what was going on, and it turns out that a much better way to solve this kind of problem is actually to take a little bit of inspiration from neuroscience. So when humans perceive a scene, it's actually widely hypothesized that we actually have 2 streams of visual processing, a spatial stream and a semantic stream. So this is sometimes referred to as the dorsal stream and the ventral stream. And in our design, we also have 2 separate streams for this neural network, a dorsal stream that tries to figure out whether the grasp will succeed, which largely involves kind of spatial processing, and a ventral stream that tries to figure out what is it that you're grasping. So this is primarily reasoning about object categories without having to worry so much about the spatial relationships between the objects. And that turns out to work actually quite a lot better. So how well does it work? Well, again, we have a testing setup where we have a number of different bins with test objects that were previously unseen during training, but from the same categories. And then we're going to basically give the robot a sequence of randomly chosen classes. We use the same random seed for each experiment, obviously, so that it's consistent, but it's chosen at random. And we give it the sequence of these commands and then evaluate its success rate on average. So we tell it, pick up this thing, pick up the Lego, pick up the toy, and so on. These are the results. So this task is quite a bit harder. So before we were seeing success rates, in the 70 to 80% range. Here we're seeing success rates that, in the best case, only get up to the high 30s. So it's quite a bit more difficult because you have to actually pick up an object of the right class. You have to both pick it up successfully and get the right type of thing. But there's actually quite a bit of benefit from a few interesting design decisions, like using the 2-stream model, which here you can see is at least twice as good as the basic one. And then the 2 bars on the far right are actually incorporating auxiliary data. I didn't have time to cover this in detail, but one of the things we can do is, because we separated the model into 2 streams, we can actually add data that has semantic class but doesn't have the grasping information for training the dorsal stream, and we can add data that has grasping but not with semantic labels. For example, objects that are of different categories that are not one of the n. And that turns out to also improve results quite a bit. All right, so that's it for the first section. Now, so far I talked about how we can self-supervise large-scale reinforcement learning experiments where we're actually looking at generalization, looking at new objects and situations that the robot hasn't seen before. Self-supervised using basically domain knowledge in the case of the standard grasping experiment, and self-supervised using label propagation in the case of the semantic grasping experiment. But But what about more complex tasks? What about tasks where it's very difficult to get goal supervision or even to interpret what it is that the robot is supposed to be doing? So this is a slide that I think Chelsea probably had in her talk to explain why we might want to do, for example, imitation learning as a way to infer rewards. So in a classic kind of benchmark setting like a video game, we typically have a score that tells us how well we're doing. But in a real world setting, like for example, here in this picture where the child has to figure out how to pour a glass of water, just figuring out whether you have water in the cup is like a very difficult computer vision problem. So you need to do a lot of work, a lot of engineering just to evaluate reward functions. It'd be awfully nice to be able to skip that step, and Chelsea talked about how inverse reinforcement learning can get us part of the way there. And I want to talk about a few other ideas there that we've explored recently, inspired primarily by work in computer vision. So one of the things that we tried, this is work by Pierre Sarmanet and Kelvin Xu, is to use visual features from, for now, a network that was just trained on some other vision task. So the idea here is to say, okay, let's take visual features that we know are good out of a network trained for ImageNet classification and see if just distance to those features can be used as a good proxy to a reward function. There's a little bit more sophistication to the method than that. What we do is we actually take a task and we try to segment into stages where different visual features should be used as the goal, so using a segmentation method. But the high-level idea is this, that if you want to get a robot to do something like opening a door, right? The task physically, maybe is not that complex in terms of us understanding what it means to succeed, but again, you have to solve like a pretty complex perception problem to actually figure that out if you're doing it from images. On the other hand, it's very easy to ask a person to just do this thing and show us what it looks like. So this task to us seemed like a really good candidate for studying the value of this method based on visual features. So what we did is we had a few humans show what it looks like to open a door, recorded the visual features at different stages of the task, basically automatically segmenting the task into stages, and then we gave that as a reward function to a robot. So I'm not going to go, this is covered at a pretty high level, but the main takeaway message here is that if you are willing to, if you can have a way to obtain good visual features, for example, from an ImageNet trained model, you can actually use that as like a pretty decent reward function using example demonstrations of humans. Okay, so that kind of got us thinking that, well, if we have some way to get these good features and we have a task that's simple enough that these features actually work, we could get away with an entirely visual evaluation of the reward using just a few demonstrations. So for this next project, this is work by Abhishek Gupta and Andrew Liu, we studied how we can actually get these kinds of representations automatically without having to necessarily get ImageNet pre-training, and we're actually able to obtain much better results than even if you had the ImageNet features. So what we thought about here is, okay, now you don't have the big ImageNet data set, you can't get your really nice visual features, so what can you get? Well, one of the things you can get is demonstrations in different contexts. So a context means something about the task, other than the task goal itself, that varies between executions. So if, for example, you're recording a person doing a task, well, maybe they do the task in different rooms, in different lighting conditions, from different viewpoints. Maybe if it's a task that involves using a tool like a brush here to clean up this mess, well, maybe you're going to use a different brush or something like that. So there's different contexts, and you can record demonstrations in different contexts, and that can help you understand what is it that's invariant for the task, meaning what is the thing that is actually relevant, the completion of the task, versus what is a distractor. And then when the autonomous system, like the robot, goes to perform the task, it'll see it in a new context. For example, it'll see it from a different viewpoint, or maybe in different lighting conditions. Something else will be different about that context. So we thought, well, can we frame this problem as one of translation? Can we actually say, let's translate between different contexts. Let's figure out if this is what the task execution looked like in the context of the human demonstrator, what will it look like in the context of the robot? So specifically, the model that we have is going to work like this. It's going to take as input the frame at time step t from the demonstration. This is denoted by OT superscript I on the left. And it's going to take the first frame in the current context that the robot is seeing. This is O subscript O superscript j. And then it's going to try to translate, predict what the execution of the task, the successful execution, will look like from this new context. So it's going to try to predict O subscript t superscript j. So it's going to try to predict what would a successful execution look like at this current time, given what it looked like at that current time for the human, and what it looked like at the first time step for the robot. And we can actually visualize this, so I'll show some simulated benchmarks first, where it's a little more interpretable. The images are a bit blurry because we feed them into the network at a lower resolution. So on the left, what you can see is a demonstration. So this is a successful execution of the task. In the middle, you can see the first frame in a new context. And the thing that changes here between contexts is the positioning of the distractor objects. So the little yellow and blue things that are placed in random places. And on the right side, what you can see is the prediction made by the model for what success would look like in this new context. Now, this is intentionally chosen to be a very simple example, where all it has to do is just copy over the distractors to their location and then simply ignore them. But you can see that it's doing a pretty good job of that. So it actually predicts the arm moving through the correct motion, and the distractors are still in the same spot where they were in the beginning. So it's kind of figured out what this task would look like in a new context. This is an example that's actually a real-world example. So here on the left side, you can see a person showing how to use a brush to scoop up some nuts in this case. In the middle column, you can see the first image seen from the robot's point of view. So here it's from a different angle. And on the right, you can see the prediction made by the model. Now, because these are real images, of course, the predictions are a bit blurry, so it can't predict perfectly, but it has the general idea of the task, that somehow the dirt needs to go away, and the brush needs to move towards the dustpan. And here are a few other images of other tasks that we've tried. So on the left column, you can see a variety of simulated tasks, mostly kind of pushing-style tasks. And on the right, you can see some real-world tasks, pushing some objects, cleaning up some mess. In the bottom, it's actually scooping some nuts into a skillet. And then we can try to use these predictions to actually as reward functions for reinforcement learning. So again, here's the demonstration. There's a few demonstrations here. Here's the predicted translation. And then we're going to take the features, the visual features inside that network, and use the distance to these features as the reward function for a system trying to perform the task autonomously. And you can see that it does this task autonomously. This one is not a very difficult task, but the same idea can actually be applied on real robotic systems. So here, again, this is a person actually illustrating this sweeping task, in this case, from different viewpoints. The model makes predictions, and in the process of learning to make those predictions, it learns visual features. So this is the demonstration, this is the target context, and this is the translation. And then you take those visual features and you track them using a reinforcement learning algorithm. In this case, this is a model-based RL using GPS, and it can actually get the robot to do the task. And we actually compared what happens if you track just ImageNet features. So that's the lower left corner. You can see with ImageNet features, it does something sensible, but doesn't succeed quite as much as with the features learned for translation between contexts. And here's another real-world task. So here, the human is demonstrating pouring some almonds into a skillet. We use almonds because we don't want to get liquids all over our robot, so you could pretend that these would be your favorite cooking ingredient. This is the input demonstration video in the resolution seen by the camera. This is the predicted translation. And then now we're going to use the visual features there for reinforcement learning, and this is the robot trying to do the task. And it's not perfect, it spills a little bit, and the way that we evaluated success is by, of course, looking at what fraction of nuts make it into the skillet. All right. Any questions about this? Yes? Yeah, this is actually a very good question. So there's actually one component to this method that I glossed over that takes care of exactly this problem. So the question was, if the training data is all successes, then wouldn't it just like, if it sees something that's completely out of distribution, wouldn't predict some like really weird stuff? So it turns out the answer is yes, and in fact, because all the training data is of successes, it actually has a bias for translating failures into successes. So one of the ways that we solved this issue is we just said, if your predictions actually disagree very strongly in terms of the pixel error with what you're actually seeing, then you get a negative reward. So you have to match the visual features, and your predictions have to be accurate. So go to places where the model actually makes accurate predictions. And that turns out to be quite important. All right, yes?
Last question. In the 100 examples, that you the robot, you cover like quite well the state possible orientation of the object, or does it still work if you present
Yeah, so the question is, do we cover sort of the range of context or not? So the answer is that the method requires, or one of the assumptions that the method needs to work, is that the distribution of context seen during training matches the distribution of context seen during testing, which is the usual assumption for any supervised learning algorithm. Now, there are a few cases where this assumption can really get you into trouble. So a person's hand looks very different from a robot's hand. And you'll notice that we used like tools in these experiments, and there's a reason for that, because we didn't want to deal with what is called the domain shift problem. So there's a separate problem, which is how do you deal with contexts that are out of distribution that is not addressed in this work, but that's something that will be very important, I think, in future work to deal with. Yes? I'm not sure. I could ask Abhishek and Andrew if they tried that. I would imagine that it would probably still go through the motion, because if the prediction is that the brush moves to the side, that's better than nothing, basically. But that's just a guess. Yes?
Just curious, you had distraction objects that it would end up avoiding. What about if it had interference objects? Like occasionally something would come by and
Yeah.
how would it react to that as a translation?
So we didn't try anything like that. My expectation is that if the interaction with the distractor was sort of represented reasonably well in the training data, so if there were a bunch of distractors all interacting in training data, and now you saw different distractors interacting in sort of structurally similar ways, then it would probably make reasonable predictions. But if you saw out of distribution behavior, then you probably get in trouble. All right. Yes? Right, and then you try to basically match the... yes, I think that would be a reasonable solution. Now, I should say one of the things, just to clarify, that we did in this work is we didn't actually try to explicitly track the pixels during reinforcement learning. The reinforcement learning reward function was distance to the features. So the features were learned by predicting the pixels, but it turns out the distance in the feature space is a much better reward. And the reason for that is pretty simple, is that if your entire image is shifted by 1 pixel to the left, the pixel values might be completely different. But so long as the underlying features are similar, then the method is happy. So I think for Atari, the same idea would work, but you would also need to pull out the features. Okay, so far I talked about how we can conduct large self-supervised learning experiments in diverse settings in the real world, for number one. For number two, I talked about how we can pull out some notion of goal so that we can then enable self-supervision. And then the third topic I wanted to talk about is how we can have systems that solve diverse ranges of different tasks in the real world and actually build on what they learned previously to solve new tasks more quickly. So if we're doing something like learning to play Pong using Q-learning, for instance, which all of you learned about, well, it requires on the order of 2 to 10 million frames to learn a successful policy for this. Maybe with a better algorithm you can get that down a little bit, but still somehow it seems like this is a lot more than what a person ought to need. So if you put a person down in front of this game, you know, they'll probably get like a pretty decent score within just a few minutes. If you let them practice for hours, they'll probably do really, really well. Maybe not quite as well as the machine in the end. Maybe their reflexes aren't as good. But still, somehow people learn very quickly. So how is it that humans can learn so fast? Well, one idea is that maybe we don't actually learn from scratch. Maybe when we learn very fast, maybe what we're really doing is we're not just doing kind of the Q-learning from a random initialization. Maybe what we're doing is we're connecting up what we're seeing now to our past experience to learn more quickly. So what can we reuse from past experience to learn new tasks? Well, one of the things that was covered in a previous lecture is model-based reinforcement learning. So model-based reinforcement learning is one of the things that we can do to reuse past experience. So if the task we're trying to solve now is different from a previous task, but it takes place in a universe governed by the same laws of physics, well, maybe learning those laws of physics is something that we can use to accelerate learning of a new behavior. So this is a video that you guys might have seen in the model-based lecture. In this method, the idea was to take some data from one of these benchmark Mujoko tasks, train up a neural network that actually predicts future states given the current state in action, and then at test time, you just use that model to choose the actions for which the model predicts the best outcome. So you take some data, you train your neural network dynamics model, then you use what we call a model predictive controller, which uses the model to make decisions. And you can do some interesting things with that. You can actually generate a bunch of random data for a swimmer, just basically flailing its limbs randomly, and then use the model that results from that data to get the swimmer to execute new tasks. So tasks that are different from any of the ones that it saw during training. So here the swimmer is using a dynamics model trained using largely random data, but at test time it's told to navigate these waypoints shown in blue. And it's not as quick, it's not as proficient as a swimmer trained with model-free learning, but it's able to execute this task on the first attempt without any additional learning. So that's usually the trade-off that you see with model-based RL. You see much more flexibility, much more generalization, but much lower proficiency. But maybe sometimes this is the trade-off that you'd like to make. And for this next one, we're going to take the ant. Same deal. We're going to have the ant generate some random data, use that to train a dynamics model, and then at test time, the ant is told to follow some waypoints that it's never seen before, and it has to actually figure out how to generate a gate that follows those waypoints. This is a project that I think Chelsea also probably covered in her slides, but we can take this idea of model-based RL and we can also do it in the real world with complex observations like images. So we could, for example, have robots interact with objects, basically playing with things, trying to understand how physics works, recording the images and their actions, and then build a model that actually looks at the current image that the robot is seeing, the sequence of future actions, and predict what the robot will see in the future. So I'll go through this pretty quickly because I think Chelsea probably covered it fairly well, but again, kind of similar story that if you can build one of these predictive models, then you can use it to push new objects in new positions at test time. So you can actually get that flexibility and generalization. And again, similar to the Majoko examples, the robot is not like super proficient at this. It's not very fast. It's not particularly accurate, but it's able to do this thing on the first attempt without having ever seen it before. Okay, so that's the model-based way of thinking about building on prior tasks, is that you can take the data from those prior tasks, use it to learn something about physics, and then take that knowledge of physics to a new environment. Another thing you can do is you can try to learn multiple tasks simultaneously and hope that the shared structure between those tasks actually improves your generalization. So this is some work done by Ruhola Rahmatazadeh and Puya. And what they did is they actually did imitation learning in this project. So I'm not going to actually focus too much on the learning algorithm. The interesting thing is the multitask setting. So here, it's imitation learning. It could have been RL as well. So that's less important. The idea is that they have a neural network that takes in images, again, for a camera overlooking a robot. It's processed by a content. It goes into, in this case, a recurrent policy, and that policy outputs actions. But the same policy is going to be trained to do multiple tasks. So it's going to be asked to put a little piece of bubble wrap on a plate, move some pliers around, push a plate off the table, pull a little box around on the table, use a little rag to clean off a box of screwdrivers. So kind of tasks that are all different, but they share some components. Like many of the tasks involve some kind of grasping or pushing. So there's pieces that appear in multiple tasks. So as I said before, it's an imitation learning method. So to generate training data for this one, actually a person just illustrates the task using a video game controller. So here you can see the human is demonstrating the task. And then the human demonstrates maybe several hundred demonstrations for each of the 5 tasks, and that's used as training data for the robot. So it's used to train this network that involves a convolutional encoder, regularization via an autoencoder mechanism, and then a recurrent policy. And then once it's trained, you can actually just let it run, and it will use images to try to perform whatever task basically is set out in front of it. So here, there's a rag in a box, and it picks up the rag and tries to clean off the box. And it wipes it a couple of times before it decides that it's all good, and now it's going to put it back. A person can come in and perturb things a little bit, and it will try to find the object and try to perform the task. So it's diligently trying to do its duty. Okay, so that's nice. It can kind of do this stuff, but the interesting thing for us in this experiment is the multitask setting. So there are a number of different conditions that were tested, including a single task condition where a separate network was trained for every task, and a variety of different multitask conditions. So the first multitask condition is one where all the tasks are given to the same network. The third row there adds the autoregressive estimator, which allows it to represent multimodal action distributions. That's very important in imitation learning. And the last one also adds this reconstruction regularizer. So these are just kind of different variants of the model. But the important 2 rows to look at here are these 2. This is what happens when you go from having a separate network for each task versus a single network for all the tasks. And you can see there's actually a pretty big jump in the success rate. This is a % success rate over multiple trials. A pretty big jump in success rate for 4 out of the 5 tasks. And in some cases, the jump is enormous, like for task 4. So there's a lot of sharing that actually happens between these tasks. And this agrees with our intuition from the earlier experiments on robotic grasping. And then once you put in all the bells and whistles, you can actually have it succeed at a pretty high rate. Okay, so far we talked about the model-based approach to building on past tasks, as well as the multitask setting where you actually put multiple tasks to the same network and hope that the interaction of those tasks gets you better generalization. But we haven't talked so much about using past experience to learn faster. So as I said before, with something like ImageNet, a big diverse task, it's large scale, it emphasizes diversity, and it's evaluated on generalization, whereas reinforcement learning benchmarks tend to be small scale, emphasize mastery, and evaluate on performance. Is there a way that we can set up a reinforcement learning problem, but then specifically ask for generalization, specifically try to optimize for a representation or a model that can generalize well and that can learn quickly in new settings? So there is kind of one example that we have of an approach to building a model that can learn new tasks quickly that just happens to work, and that example is in computer vision. So if you do train your big convolutional neural network on ImageNet, and you take the features inside that network, just pull out those convolutional features, and then you use those features to solve a new task, for example, using logistic regression or using just a small neural net, it turns out that they work really well. Like it's almost kind of amazing how well these features that were trained for classifying a 1,000 class for LSVRC will allow you to solve new visual perception problems. Now, it's not that we specifically did something magical in training that content, we just trained it with regular supervised learning. So in some ways, there's a property of ImageNet being a very good data set for visual perception tasks. So maybe that's kind of bad news if you want to solve things that are not visual perception tasks. But can we somehow force the network to learn ImageNet-like features that are good for fine-tuning? So where are the ImageNet features of decision-making? So what we can do is, instead of hoping for the best, instead of hoping that we can get the right kind of data set for our task, maybe we can actually ask a model to be a good model for subsequent fine-tuning on a new problem. So I'm going to tell you about some work. This is actually work done by Chelsea Finn for a method that does essentially this. So the idea is the following. If you're solving a single reinforcement learning problem, like you're trying to get the ant to run, what you're going to do is you're going to generate samples from your policy. You're going to use those samples to estimate the gradient of your reward, for example, if you're using policy gradients. And that's going to give you a new parameter vector that hopefully is better than your last one. So now let's go to the multitask setting. Let's go to the setting where maybe the ant needs to run in all sorts of different directions. And you'd like to have that ant be able to learn to run in new directions more quickly. Well, now what we can do is we can generate samples of the ant running in all different directions. And we can say that we know that if we wanted to learn to run in a new direction, we're going to use policy gradient, right? So now instead of asking the model to be good at running in all possible directions, we're going to say, if we're going to adapt the model with policy gradient, let's find a model that is good at being adapted with policy gradient. So that after one gradient step on any one of these tasks, it actually achieves the best performance. So this is a little bit hard to maybe to grasp right away, but the idea basically is that you don't want parameters that are themselves good at all the tasks because that's impossible. You can't have a single policy that runs in all different directions all at the same time because they're mutually exclusive. What you can do is you can say, I want parameters that when I take one gradient step on a particular task, when I take one gradient step, for example, on running to the left, I'll become as good as possible at running to the left. And you can actually optimize for that. You can say, after one gradient step, you can write down what your parameters will be. They'll just be theta plus alpha times grad theta. That's gradient descent, or gradient ascent in this case. And then you take the gradient of the reward of those parameters. So there's actually a little typo on the slide. That first gradient operator needs to have an Ri after it. So it's the gradient of the reward of the task after one gradient step. If the math here doesn't quite make sense, we can also try to visualize this idea. So here where you can see the thick line is showing the path of the parameters through the parameter space. And at every step, what you can do is you can consider where the parameters will end up if you take one gradient step on any one of the tasks. So here there's 3 tasks, for example, in this illustration, and these little arrows here show what happens after where the parameters end up after one step. So if you take a step on task 1, you'll end up here. If you take a step on task 2, you'll end up here. And what you're trying to do is you're trying to put these parameters theta in a spot where one gradient step will get you as close as possible to the optimal parameters for that task. And it doesn't have to be 1. You can do some small number, 3, 4, 5, and so on. So let's look at what this algorithm actually does for some simple benchmark tasks. So what you can do is you can take your ant, and you can look at the policy that you end up with if you run this algorithm with the different tasks corresponding to running in different directions. So this is not the policy that's actually good at running in any one direction. This is sort of the policy that is ready to learn to run in any direction. So this is the policy before the gradient update. So let's watch it again. You can see that what it's doing is essentially kind of running in place. So it's not going anywhere in particular, but it's exhibiting this behavior that's actually good for figuring out how to run in a particular direction. So it's sort of running in place, it's ready to go. And when we give it one iteration with a reward that rewards running forward, it immediately then takes that gradient step and figures out how to run forward. And if you give it one iteration with a reward to run backward, it again takes that one gradient step and figures out how to run backward. You can do the same thing with other systems. So this is the same experiment done for the cheetah. Again, the initial policy that has not been adapted yet to any particular task, it sort of runs in place. And then if you give it the reward for running backwards, it starts running backwards. And if you give it a reward for running forward, it starts running forward. So these are just kind of toy examples. These are not meant to be particularly diverse. Oh yeah, and it also does a cartwheel to celebrate. They're not particularly diverse, but it's just evaluating that, yes, you can do this thing with policy gradient, and you can actually have, even though policy gradient is not a very efficient algorithm, you can get it to become efficient if you specifically train for efficiency, if you specifically learn to learn. One of the things that we did to study more diverse tasks with this algorithm, this is actually an experiment that uses imitation learning rather than reinforcement learning. But again, the focus is on the model and the adaptation. We could in principle try to do this with RL as well. Here the setup is that the robot, the simulated robot, needs to observe a single demonstration provided by a human that shows a particular object being pushed to this red location. And the protocol here is that each time there's two objects in the scene. At test time, they're again objects that have never been seen before, and the robot needs to figure out which object to push to the destination, just from looking at the demonstration, from the raw pixels of the image. So there's a demonstration, and then the policy needs to generalize to new positions with that object. So the demonstrations look something like this. At training time, the robot sees lots of demonstrations of pushing different objects. At test time, it sees new demonstrations with new objects. So at training time, it needs to use these demonstrations to perform this meta-learning procedure to figure out a parameter vector for the network, such that when it's updated with one gradient step on one of these new demonstrations, it'll do as well as possible. So then again, if we take that one gradient step with the demonstration, then we can get it to figure out how to, in this case, push the green teddy bear. Looks like the other videos are having some trouble, but yeah, basically it's exactly what you expect. So it can push the green teddy bear, and it can figure out to push the other objects here. So some technical issue, but yeah, basically you'd have to take my word for it regarding the brown and yellow cupcake, if that's what that is. All right. So I talked about how we can self-supervise real-world tasks. We can actually run large real-world experiments that actually emphasize diversity. I talked about how we can get to this ability to self-supervise from human demonstrations, and how we can build on prior experience to learn more quickly or to generalize better. So for the last portion of this lecture, and I guess to conclude this workshop, one of the things I'd like to do is I'd like to discuss a little bit how some of the things we've learned might help us work towards being able to build intelligent machines. So there's a very pragmatic reason to want to study deep reinforcement learning, which is that it can be a useful tool, perhaps for a range of different problems, including some of the robotics problems that I discussed. But to me, at least, there's a much more fundamental reason to want to study these topics, which is that perhaps part of the secret to actually building intelligent machines might lie in methods that look like deep reinforcement learning. So let's take a step back a little bit and imagine that you want to build an intelligent machine. And forget everything you learned in the last 2 days. Let's just say your job is to build an intelligent machine, a machine that is as intelligent as a person at the kind of diverse real-world tasks that we might encounter. Where would you start? Well, you might say, okay, a person's brain has a number of functionalities. You know, a person needs to be able to see, they need to be able to hear, they need to be able to move their limbs, they need to have language, and so on. So we'll say, okay, there are a bunch of these little boxes, little modules, and we'll, get a team of engineers, sit down, code up for a while, and try to implement each of these boxes. And maybe the picture on the left is sort of intentionally facetious and naive. Our modern view of the brain is a little more sophisticated, but same story. We can say there are a bunch of parts, let's go and implement each of those parts. Now, unfortunately, that doesn't tend to work very well. So this was kind of the first generation of AI methods that sought to basically implement directly the functionality of different parts of a machine brain. So maybe we don't need to implement these parts directly, maybe we should use learning. And that's a lot of what we learned about in the last few days. And maybe we can think of learning as kind of part of the basis of intelligence. There's good reason to believe this might be the case. There are some things that we can all do well that perhaps we might reasonably believe to be innate to human ability, like walking. But there are some things that we can only learn, like some things that we can't possibly come pre-built with, like driving a car. So that's clearly something we learn. And we can learn a really huge variety of things, including very difficult things. So therefore, our learning mechanisms are likely powerful enough to do everything we associate with intelligence. Now, this is a guess, this is a hypothesis. It's not necessarily true, but maybe it's a hypothesis that we can work with for now and see where that takes us. Okay, so now we say maybe learning is the basis of intelligence. So how do we then implement the brain? Well, maybe we need to implement a little learning algorithm for every module. So we don't have to program the vision system ourselves. We just need to build a learning algorithm that can learn to see, another learning algorithm that can learn to move, and another one that can learn to hear. But do they really need to be different learning algorithms? Maybe there's a single flexible algorithm that we can build that can do all of these things. At least when it comes to perception, there's some reason to believe that this might be the case. So there are a number of experiments that you can do to try to understand how the human brain perceives using the senses. For instance, you can take an electrode array, pipe in input from a camera into that electrode array so that the little pixels on this array are electrified based on what the camera is seeing. You can put it on your tongue, and with a bit of practice, actually quite a bit of practice, you can actually learn to perceive the visual world with some low degree of acuity using this electrode array. So you can essentially learn to see with your tongue at a very, very low resolution. Humans who are blind can often get a reasonable sense of their environment using sound. And one of the more compelling experiments along these lines, this is sometimes referred to as the ferret rewiring experiment, actually showed that the auditory cortex in ferrets can learn to see. The way this experiment was conducted is that they took ferrets at a very young age and they conducted a little surgery on them. They took the optic nerve and disconnected it from the visual cortex and reconnected it to the auditory cortex. And then they had them grow up there and tested them for their visual acuity, and they found that indeed ferrets who had their optic nerve reconnected to their auditory cortex did develop some base level of visual acuity, meaning that their auditory cortex could learn to see. So that's very interesting. Now, why would this be the case? The natural ferrets never randomly have their optic nerve reconnected. So for whatever reason, the brain found it quite useful to have a single learning algorithm, perhaps, for all of its sensory cortices. And maybe the story goes a bit further than that. Maybe it's actually a single learning algorithm for all of the parts. So if there is a single algorithm for all the parts, what does it need to be able to do? Where it needs to be able to interpret rich sensory inputs, because we've got those, and it needs to be able to choose complex actions, because the only way that we affect the world around us is by taking actions, by moving. So why deep reinforcement learning? Well, reinforcement learning is what can reason about decision making. That's the part that lets us figure out how to take actions. And deep models are the models that allow our algorithms to learn and represent complex input-output mappings. Or put another way, deep models are what allow reinforcement learning algorithms to solve complex problems end-to-end. That is not to say that what the brain does is deep reinforcement learning, but rather that deep reinforcement learning methods perhaps have a non-trivial shot at being able to have that kind of functionality. Okay, so maybe that's part of the dream, but where are we at now? What can deep learning NRL do well now? Well, so far we've seen that we can acquire a high degree of proficiency in domains governed by simple known rules, things like playing Go and playing Atari games. We can learn simple skills with raw sensory inputs given enough experience, things like the robotic skills that I showed. And we can learn from imitating enough human-provided expert behavior. So in the imitation learning lecture, you probably saw the NVIDIA driving video, so we can learn things like that. What has proven challenging so far? Well, humans can learn incredibly quickly, and I talked about a few experiments that allow learning algorithms to build on their past experience, but there's still a long ways to go there, and deep RL methods are still usually pretty slow compared to humans. Humans can reuse their past knowledge, so transfer learning in deep RL is still an open problem, and it's often not clear what the reward function should be. So this is actually something that seems to be pretty clear-cut for humans, but a little difficult to nail down for our machines. It's also not clear what the role of prediction should be and how model-free algorithms and model-based algorithms should interact. So there's a lot of evidence that the brain does a little bit of both, but it's not clear how the two are reconciled or whether they're actually two symptoms of the same underlying cause, a single algorithm that actually exhibits both properties. There's another thing that's perhaps missing from reinforcement learning that takes maybe a little bit more effort to understand. This is a slide that I shamelessly pilfered from Jan LeCun. But I think it's a really good slide for illustrating one of the deep questions or challenges in reinforcement learning. So I'm going to kind of colloquially refer to this as Jan LeCun's cake. The point of this slide is that there's a kind of an information theoretic reason to believe that reinforcement learning might not be by itself a very good way to learn very complex things. And it's an argument about sample efficiency. Basically, how many bits of information do you get from each sample that you observe? So in reinforcement learning, what you observe is your input, your observation, your image, or what have you, and you get the reward. The reward is a relatively small amount of information. In fact, in many of the really interesting tasks we might be interested in, maybe the reward is even binary. It's just 1 if you did it right and 0 otherwise. So as little as 1 bit of information, and that bit is usually 0 anyway. So the amount that you get from every sample is pretty small. If you're doing supervised learning, like ImageNet classification, well, ImageNet has 1,000 categories. That means there's about 10 bits of information in every supervised sample. There's a lot of input, but there's a very small amount of output. On the other hand, if you do something like prediction, if you, for example, try to predict the future, now the amount of bits of supervision that you're getting for every single sample is enormous. If you're predicting, let's say, images that the robot will see next, or like all the stock data for the next 1 hour, like that's a lot of information, a lot of bits of supervision. So maybe that's something important in there, that if we really want good sample efficiency, we want to be able to drop a robot into the jungle and have it learn from scratch how to do all the complex things that a person or animal would do. Maybe it needs to do more than just reinforcement learning. Maybe it needs to draw on all this additional supervision that's available to it. Or maybe not. So where does the supervision come from? Where can we get more supervision? So one very reasonable hypothesis is that we need to really think about eating that entire cake. So we need to think about unsupervised or self-supervised learning in addition to reinforcement learning. We need to think about modeling and predicting the future, or building generative models of the world with unsupervised learning. So there's that way you have a lot to do before you even accomplish a goal. Before you see the first reward, there's already a lot of learning that you can do by predicting and generating. But that's not the only hypothesis, I think. I think there are a few other potential answers. One potential answer lies in imitation and understanding other agents. So perhaps it's not an accident that the one example we have of an intelligent species on this planet is also a very social species. And perhaps we have culture and we have complex societies for a reason. Maybe it's not just an accident. Maybe it is, in fact, fundamental to intelligence. We don't know that for sure, but perhaps. And if that's the case, maybe imitation learning plays a much more central role than any of us might suspect. And then there's another hypothesis that perhaps is not unreasonable, which is that we just need a good enough reinforcement learning algorithm. So I'm going to kind of refer to this as the giant value backup. The fact is that even if your reward is something binary, in reality, if you're learning something like a value function or a Q function, there's a lot of information in there. You know, the whole point of the Bellman backup is that once you see something that anticipates a future reward, you will get that signal before you observe the actual reward. So as you learn more and more, the signal becomes more complex. And maybe that's actually enough. We just need to develop a better reinforcement learning algorithm. Or maybe it's all of the above. So I don't know the answer to this, but these are some hypotheses that we might think about. So just to conclude, let me say a few words about how I think, some of the things we should keep in mind as we go about answering these questions. One of the things that I think is really important is to pick the right problems. So there are a lot of really good reinforcement learning benchmarks, and some of them you guys used actually in some of the work in this workshop. But I think that it's important to look for tasks that really have the characteristics of the real world, whatever real world means in the context of your favorite application. And in fact, there are very nice kind of benchmark suites that are coming out that do emphasize diversity a lot more, things like OpenAI Universe, and of course you can go out and get your own robots, or you can look at other kinds of diverse tasks in terms of video games or things that your agents can do on the internet. So think really hard about picking the right problems, the problems that have the characteristics of the real world tasks that really matter. Pay attention to generative models and prediction. I don't really know whether Jan LeCun's cake is the right way to look at things, but it seems like there's a lot of merit to that, and it seems like we shouldn't ignore all that rich knowledge that we can get from learning to predict or generate sensory observations. And I think it's really important to carefully understand the relationship between reinforcement learning and other ML fields. So in many ways, deep reinforcement learning came about as a confluence of deep learning researchers looking at reinforcement learning problems and vice versa. And we don't know where the next big innovation in RL will come from, but it seems quite plausible to think that it will come from other ML fields that might interact with RL in the future.
Okay, let's thank Sergey again.